Hey there, it's Codeforces Round 957. Five times. Okay. So this is better. Oh, come on. Yeah, I need to rewrite this. Okay. Oh. What do I need to end? I don't need n. Show down this. Not less than k, not greater than m. Okay. The sum of fi's minus the sum of gi's. Oh, this is just easy gradient. Very simple gradient. So you want more f and you want less g. So what does that mean? this one. Okay. Oh, in total. For sure, just do a crease strategy or read it. Jumped up to N. We should greedily go to these small. said yes to this? Wait a minute. Oh, I didn't do the keychain. What the hell? What the hell is this? So n times a minus b has to be tiled with n. N times a is at most a million. That's 6, right? Wait, so now we can do a. N times a minus b equals value, so it would just be n minus. Well, b is definitely n most. And L times A minus B equals 1, then yes, now we're actually good. Oh, this is okay. Huh. Wait, sorry, what? Oh, let's see. Okay. So next we track the prime counts and once each one is. We have to not take center. Yeah, so then yeah, that works. That works. So or you take the product of GCD with X. That is even easier. Okay, got it. Is that it? Oh, exactly x. The property has to be exactly x. Hmm. We have some knapsackish type thing going on, so obviously. How complicated can we get up to? 100K. $128 divisors. Oh, I see. We just kind of DP that. Okay, got it. So Oh, that's gross. Why is this wrong? Why is this wrong? Oh, that's tricky. I was supposed to use it more than once. That's gross. Okay, this should be correct. What? Sum of next. Just take every subset b on b plus 1. So 2n plus 1 is, what was the answer for this? 2n plus 1. Oh yeah, it's really 2 times size plus 1. It doesn't really matter. So given that we pick a size, we pick a size. Let's see what difference is. 3. Four, 5, 6, and 7. For it to be a particular number, right, so it's just like this. How many ways are there for this to be answered? So it has to be not picked. And then, well, obviously this is also inside. There have these size plus 1 that are not picked. And is that the answer? No. 2. What? Should be. I'm down by 1? What is that? I don't know why, but apparently. That's not right. It's 3. Okay, can I figure out what's wrong with this? So size is 1 and the max is 2. Size is 2, the max is 3. Oh, are you including the empty subset? Oh wait, 1 is 4. Okay, then this is just right. Yeah, if I don't do this, I don't work. They all don't work. Okay, cool. All right, so we won this contest. And actually, hang on. Actually, one more. Cool. All right, so we won this contest, and yeah, it's a nice little set of problems. Let's go through them. Cool. So start with problem A, and basically we're doing A times B times C, and at most 5 times we can pick one of the numbers, and increase by 1. We want to maximize the product at the end. Yeah, this is just a simple greedy. Basically, the idea is if you have A times B times C, basically we're always going to increment the smallest number. Because if you do this, A plus 1 times B times C, you get a times b times c plus b times c. So obviously, the greedy idea is to have these two be the biggest two out of the three. This doesn't prove that doing it 5 times this is the right strategy, but that also happens to be the case. It is still the right strategy, even if you repeatedly iterate. But yeah, if you don't believe that, you can also just try all the different options for spreading out how to do adding 5. It's not that many. I guess probably some people wrote like code that just, you know, it's like ABC, and then they just take the max of a plus 5 times b times c, and a plus 4, just a whole bunch of things. That could also work. Obviously, it takes a little longer. But yeah, this code, pretty simple. Just find them in, increment it, and then you're done. Cool. Yeah, I'm just going to go through these pretty quickly. Right, B. Yeah, so B, you can break things. You have a bunch of, what is it? Sticks, kind of, and then you can break one into 1 and a minus 1, or you can attach 1 to something. You want to combine everything together. Yeah, so this is another greedy. The idea is we're gonna combine everything into the longest one, because, I mean, yeah, basically everything else has to become just 1 since you can only merge 1s. And the longest one is the best one to keep intact. So that's what we do. We just sort everything, and then for a given value of a, if you need to, yeah, if you need to break that up into 1s, that takes a minus 1 steps. So for example, if it's 3, you need to break into 1 and 2, then you break the 2 into 1 and 1. And then afterward, you need another a steps to combine with the biggest one, because you're going to 1 by 1 merge each of the ones. Yeah, and that's it. You just add this up, and you're good. That's the answer. In fact, I don't even use n, so it's a little silly, but yeah, that works. You can do this in linear time instead of sorting, because you only need to find the max element. It doesn't matter the order of the other ones. You just need to find the max. Cool. That's B. Moving on quickly. C. This is, yeah, you want to maximize the sum. The problem statement looks a little scary, but if you just think about it, you just want to maximize the sum of f minus the sum of g. So you just want to increase f as early as possible and increase g as late as possible. And yeah, I mean, this is just a simple greedy. It turns out those two goals don't conflict, because basically you can almost just put a reverse sorted permutation where, yeah, you use the biggest number as possible first, which means you increase f as quickly as possible first, because f is the sum of everything at least k on the prefix. So yeah, so you want the numbers as early as possible, you want them as big as possible. So reverse permutation makes sense there. And then the only thing is that for g later, you want to increase as slowly as possible. So you actually want to, because basically for g, it can add up the numbers 1 through m, you actually want to reverse 1 through m. So for example, for 10, 3, 8, what I would output is 10, 9, it's not exactly this, it's similar. 10, 9, 8, 7, 6, 5, 4, 1, 2, 3. So you can see that, you know, here, this is the key thing, having 10, 9, 8, and having 1, 2, 3 here. The order of these numbers doesn't matter, that's why in the output, the sample output, they do this. But yeah, basically what I do is make this permutation, 1 through n, reverse it, now it's n through 1, and then I reverse the last m values. So it'll be n through m plus 1. This is very confusing sounding. Then 1 through m. That's what it's going to be. Cool. That's C. D. So D, we are jumping and swimming across, not across, through, I guess, through a river. We can only swim k meters in total at most. We can jump up to m, but only from land or logs, and we have to avoid crocodiles entirely. Yeah, so again, this is just a greedy strategy. This is a lot of greedy problems. Basically, yeah, for convenience, I put an L on both sides, so the banks are logs, essentially. If we ever end up on a crocodile, we lose. Otherwise, if our current thing is water, we have to swim 1 step ahead. And then otherwise we're on a log, and we can do a jump. So for the jump, The greedy idea is if there's any log we can reach, we can jump to, we should jump to the log, because it's always better to be on a log, because you can jump again. Otherwise, we jump to the farthest water we can get to. Farther is better, because then that way we do less swimming. And then if we can't reach log or water, then we can only reach crocodiles, which means we lose. Yeah, so just pretty simple there, just a greedy approach. Yeah, just need to convince yourself the greedy is correct, and then implement, and you're good. Cool, and then yeah, the fact that m is small helps with the time complexity being small. But yeah, you could actually speed this up if you needed it to be faster, but at least for this problem, you don't need to do that. All right, problem E. Okay, yeah, this is a weird one. Basically, you're given n, and you want to compute how many pairs A and B there are where n times A minus B is equal to this incorrect calculation of n times A minus B, which is you take n, concatenate it A times, and then you remove the last B characters from the string. And n isn't too big, only up to 100, but A and B can be up to 10,000 each. So you can't just iterate over all A-B pairs, because that would be 100 million. That's too many. So instead, if you think about it a bit, you need this value to be, it has to be a prefix of n concatenating with itself over and over, right? And also, it can't be that big, because this is at most 100, and A is at most 10,000, which means it's at most 1 million, and then minus B, which is at least 1. So it's less than 1 million, for sure, which means it has at most 6 digits. So actually, there's only 6 prefixes of this that could make sense. So what I first do is I iterate over the length of the result. And then take the string v. That string is just going to be, our numbers, digits over and over until length. And then now I know our goal. This value is our goal, right? And so now that I know our goal, what I can do is I can iterate only A, and then I know what B is, because I need n times A minus B equals value. So B is just n times A minus value, right? So we get this. And then we just need to double check. B has to be between 1 and 10,000. You don't actually need to check this part, A times n, because you already started with this. And then, yeah, then we need the length thing to work. So we need the length times A minus B to be the number of digits we're going for. If both of those are true, then A and B works. And so, yeah, that's it. So this is just, instead of 10,000 squared, we just do 6 times 10,000, which is much better. And yeah, that's definitely fast enough. And yeah, just output them, and we're good. Cool, that's E. I'm going to change. Also, okay, I guess they just got a lot of confusion around this. Cool, problem F. We need to we have a list of numbers. We need to separate the numbers into segments, where in every segment, the segment is bad. Bad means there's no way to pick a subset of the numbers where the product equals exactly X. And you're also guaranteed no number equals X, because otherwise there's no way to win. And you want to know the minimum number of bad segments you can make, because obviously you can also just make n segments and then that would work. Cool. So this is actually, again, it's a greedy, where you basically you start your segment at the beginning of the array, and you go as far as you can until the segment becomes bad, and you cut it off right before it becomes bad, and then you just repeat that. The only thing that's tricky here is how do you determine whether the segment is bad or not? The way I do that is it's like a DP on the factors of X. I just determine which factors of X we can create as a product. And then once we do hit X, we have to break it off. So I did this. This is maybe a little bit faster performance-wise, but it takes a little longer to code. I have a sieve. I sieve up to 200,000, and then factorize X. I find all the factors of X. there are at most 128. And then I just go through and I just do this dp. So basically, I try multiplying the factor that already works with my current number a, see if that produces a product that is also a factor of x, and if so, set the thing to true. In retrospect, though, I realize this is probably not the ideal implementation in terms of like finishing quickly. I actually think, okay, let's rewrite it. I think it would be better to just do a set. So it's gonna be slower for sure, but that's okay. I don't think it's a big problem. So here we go. So set int factors equals 1. I guess we could also do a vector. Maybe that'd be good for points. Type issue, but we'll just do that. Cool, and then we'll sort x factors and factors. Swap, I guess. Oops, here. And then if it's factors back equals x, if I have x, this is running this. This should work. This is much shorter code. All right, so I should have done this. It's probably fast enough to, well, this will take a while. Yeah, I guess you can also do this as a set. That would also work. A lot of options here. Let's try the set version. I kind of like the vector version better, personally. Yeah, so that's not too slow. That is slow. That is slow. So, but you get a lot of time. A lot of time, so it's okay. What did Manny know what his runtime was? 93. Okay, he didn't use the set then. Interesting. Anyway, it doesn't matter. He doesn't count. So, cool. Let's go to G. Last problem. Yeah. So for G, we're trying to add up the mex of B, the B plus 1, or like size of B plus 1 mex of B for every subset B, including the empty subset. They didn't make that very clear here. But yes, so turns out this is actually pretty simple. You just iterate over the size of your set. I actually could have done this. Could have just iterated from 0. I think this should work. Let's see. Iterate over the size of your subset, and then iterate over the mex that you're looking for. Now the mex is for sure at least this, right? So it's at least size plus 1, and it's also at most 2 times size plus 1, because at most sizes of the numbers are blocked. So we can just iterate this, and this is just n squared right here. And then we just need to count the ways. So this is actually pretty simple. The number of things less than max that you have to have picked is max minus size plus 1, because when max is size plus 1, you can't pick anything. And when it's 2 times size plus 1, you have to pick all size to be less than max. And then, yeah, in between, same thing. So we just do choose of max minus 1, which is how many numbers we have, but also we can't go more than n and pick those. And then if we haven't picked everything, we need to choose the number, or we need to multiply by the number of ways to choose size minus pick, the remaining, out of n minus max, which is also the remaining number of options. And that's your number of ways to do it. And then multiply that by max, and you're good. So pretty simple. And also, of course, max itself is never picked because it's the max. So yeah, that's it. Super simple. You just need a way to compute the choose functions. And here, I just pasted that in my version. So yeah, that's it. Yeah, so I actually thought G was pretty easy, easier than F, but it took me a little while to get past the empty subset thing. I actually had my code outputting the answer -1 for every test case for a sec, so that was a bit fun. But anyway, cool. Nice little contest, and nice to post a video again after a while. I know it's been a while, but anyway, hope you enjoyed it, and see you in the next one.